Good morning, Fraser. All right, so once again, the goal here is just to make sure you understand how to calculate work and how to do work, okay? So, all right, so just as a quick reminder that when you do work on an object, you're changing the energy in some way, okay? Anytime a force does work on an object, you're changing the energy in some way, all right? Sometimes you're changing the total energy. Sometimes you might be converting GPE to KE or GPE to EPE or whatever. But in some fashion, work changes energy, okay? So again, we'll get into the specifics of exactly how that works later. For now, I want you to know how work is done, all right? So here's the deal. Couple things about work. This slide is copied from your notes from last year, so this should hopefully be a little bit of review. All right, so remember, work changes the object's energy in some way. All right, so it means at least one part of this equation is going to change anytime a force does work. Okay? Now, in order for that to occur, there has to be a force doing the work. All right, you have to have a force doing the work. And in order for force to do work on an object, a couple things need to be true. First of all, the object has to be moving. All right? If I stand here and hold this coffee cup all day long, like this, it is not moving. Let's not argue about cup versus whatever, if that's where you're going. Oh, I know, it's a typo. I'll fix it in a minute. All right, so because I'm not changing the energy of this thing in any way, I'm not doing work, even though I'm exerting force. Right? Like if I stand here and do this all day, I'm going to get tired. But according to the physics definition, I'm not doing work on this. Okay? Because the object is not moving. Cool? All right. Number two, as I'm having trouble with everybody's names today. As Teddy just pointed out, there's a problem here. So the second condition is this: in order for a force to do work on an object, the direction of motion cannot be perpendicular to the direction of the force. All right? So if you've got an object moving this way, and there's some force that's this way, that force that is perpendicular to the motion is not doing work. Okay? And as a simple example of that, if I take so if I roll like this, right now there are two forces acting on me, yes? What are the two forces? Gravity and normal force, right? Okay, but as I roll, is my energy changing significantly? No. That means no work is being done, right? Does that make sense? So yes, the normal force is holding me up, but it's not changing my energy now, right? All it's doing is preventing me from falling. Follow? Okay? So anytime a force is perpendicular to the motion, that force is not doing work. Cool? All right. So this. All right. So the next thing, I guess, is this. So your work will always be negative if the force is working against the object's motion. All right. And the work will be positive if the force is working with the object's motion. All right. Cool. And then this last part of the page, honestly, we'll deal with a little bit more, but I'm going to say it now just so that it's at least planted in your brain to maybe hopefully refresh your memory a little bit from last year. But honestly, this won't come up for a couple more sections that we actually have to do this. All right? So conservative forces, when they do work, the only thing a conservative force can do is convert either kinetic energy to potential energy or vice versa. Okay? Non-conservative forces are important because they change the total amount of energy that an object has. Okay? So hopefully that rings a little bit of a bell. Maybe just talking a little bit about conservative, non-conservative forces. Again, this is all stuff that we'll talk about more coming down the road, but I just wanted to at least throw it out now as oh, that's right, we talked about those things last year. I don't remember what they are, but cool? All right, so here's what I really want to focus on today is these equations. All right? So if you're trying to find out how much work is done by a constant force, notice I highlighted it there because it is very important. I think I did not do a great job stressing this last year. Oh, no. All right, well, you can write it in. That's weird. Yeah, I'm sorry, that happened.
emphasis when you write it.
Exactly. Okay. So last year I did not do a great job emphasizing this. Work equals force times distance only works if the force is constant. Okay? So, have you guys in math class, have you guys done dot products by any chance?
Yes.
Yes. Okay. What? Shush, Calc 27. Anybody who's not in Calc 27, have you guys done dot products?
Yeah, we did it in Algebra 2.
In Algebra 2? Okay. All right. So here's the deal. Guys. So it turns out, every time we've multiplied by a vector so far this year, we've only multiplied scalars by vectors, right? Mass times acceleration, scalar times a vector. Acceleration times time, vector times a scalar, okay? So in doing that, all you're doing is you're just making the reason it's called a scalar is because it makes your vector either bigger or smaller. It scales it up or scales it down. I don't know if that's true or not, that just clicked with me, but maybe that's true. I don't know, we'll go with it. Let's say that's why it's called a scalar. All right, so, I have no idea if that's why. All right, so it turns out if you want to multiply two vectors, there are two different ways you can do it, and the two different ways of doing it have different meaning. Okay? So last year we learned work is force times distance and torque is force times distance. You guys, does that vaguely ring a bell? Remember, torque was force times the length of your lever arm, and work was force times the distance you moved it. Okay, but they have different meanings, right? One of them is a dot product, one of them is a cross product. Okay? Sarah's giving me the what the hell is he talking about, but all right. So here's the deal. You don't really need to know the difference between dot products and cross products. Here's what you need to know. All right? So when you calculate work, all right, the technical way of thinking about it is that you're doing force dot product with distance. Okay? Here's what you need to know, though. Really what it boils down to is FD cosine theta. Okay? So in that example, theta is the constant angle between the force doing the work and the displacement vector. Okay? Follow? Okay. So, shoot, I just did an example with my honors class that I wonder if I should take a minute and do with you guys. Let me see what I got next year in the notes. Yeah, I'm gonna do a brief tangent here. I think this really helped my honors students, and I think we didn't do a great job presenting this last year. So, all right. So let me do 4 real quick examples. All right. Example 1. Force parallel to distance. All right. So simple example. Suppose we've got this. Suppose we've got a box, and Roy pushes it with a force of, I don't know, 40 newtons. All right, and maybe he pushes it so that it moves through a displacement of 3 meters. Okay, so what the question would be, how much work did Roy do? Okay, so to calculate the work done by Roy, we're going to take the force that Roy exerted, dot product with the displacement that causes. Sorry, I realized I have mixed notation here. I've got displacement is delta x and displacement is d. So in this chapter, if we write d, that means displacement. Okay, so basically then what this means is it means take the magnitude of Roy's force, multiply it by the magnitude of your displacement, and multiply that by the cosine of the angle between them. Okay, now, because they're parallel, look, you guys, here's my force, here's my displacement. What's the angle between them? 0. Because there's no y component for either of them, right? So this becomes the force of Roy times the displacement times the cosine of 0 degrees. What's the cosine of 0 degrees, you guys? 1, right? So this is the force of Roy times d. So last year, most of the examples we did had the force and the displacement in the same direction. So we usually just did work as force times distance. Good? All right. So for us, the force of Roy was 40 newtons. The distance we moved it is 3 meters. Multiply this, it gives you 120. The units do work out here. You get kilogram meters squared per second squared, which is how we defined a joule. Does that make sense? Good, Dan? And you guys good? Yeah. Everybody good with this? All right, now, example 2. This time the box is sliding. We're still going to have the same displacement of 3 meters, but this time Roy is trying to stop it. All right? So, the work done by Roy is equal to the force of Roy dotted with the displacement, which is really force of Roy times distance times cosine of theta. Now, when you use this equation, you guys, because I stopped putting my vector hats over here, what that's telling you is you ignore any positives or negatives, and you just let the trig do the signs for you. Okay? So watch what happens. If this is my displacement vector, and this is my force vector, what's the angle between those two vectors, you guys? 180, right? My arm doesn't bend that far over, but does everybody see that that's 180 degrees? Okay? So we're going to get the force of Roy times the displacement times the cosine of 180 degrees. What's the cosine of 180, you guys? Negative 1. So you get negative 1 times the force of Roy times the displacement. So you get negative 1 times, oh shoot, I changed my force to 120. That was a mistake. I wanted that to still be 40. Whatever, you can leave it at 120 if you want. Just then you got to multiply it by yourself. Are you going to make it?
I don't think I can do that.
All right, so that gives us negative 120 joules, right? Follow you guys? Everybody happy? Why is it negative? Because it's opposing the motion. So we're going to, in some fashion, we're going to lose energy. We'll worry about that later. But it's opposing the motion, right? And a minute ago we said if the force opposes the motion, the work is negative. That's why. Good? All right. Oops. Example 3. Let's just have the box sliding along. All right, so whatever. My displacement's going to be this way. Here's my normal force. Okay, so let's find the work done by the normal force. Well, that's my normal force times my displacement times the cosine of theta. And what's my theta going to be here, you guys? 90 degrees, right? Because the displacement's that way, the force is this way. So you get normal force times displacement times the cosine of 90. What's the cosine of 90, you guys? 0. So if your if your displacement is perpendicular to your force, then the work is 0. This is why. Good? Do you guys agree that your normal force will well, I guess that's not necessarily true. Never mind. Usually, though, your normal force is perpendicular to your displacement, right? Clear? All right. So, now, if the angle's at a force, I'll do an example of that in just a second. Okay? So, any questions with those couple examples? Okay, so, did we hit everything here? So this component does no work. This component does do the work. No. Work can be negative. I think we hit everything there. Okay, cool. All right, if multiple forces do work, then the net work is the same as the work done by the net force. All right, so the net work is equal to the work done by force number 1 plus the work done by force number 2 plus the work done by force number 3. Oh, well, that's the same as force 1 times the distance plus force 2 times the distance plus force 3 times the distance. Factor out the distance, and you just get net force times distance. Cool? So to find net work, this is a big idea, guys. To find net work, there are two ways of doing it. You can add up the individual works, or multiply your net force by your displacement. Or use the work equation with your net force, I should say. Follow? All right, so let's do an example that has actually some more stuff going on, all right? So here we go. A 50-kilogram box of donuts, a lot of donuts, sits at rest on a warehouse floor. It says Roy pushes the box using a force of 400 newtons. I don't know why there's a dot there. Using a force of 400 newtons at 30 degrees below the horizontal. If he pushes the box 6 meters and the coefficient of kinetic friction is 0.25, then we're going to find this stuff. Okay? So, probably a good place to start would be by making a free body diagram. Yes? Always. Okay, so let's see. Roy's force. Nope. Roy's force is 400 newtons. Okay, there's going to be a vertical component and a horizontal component. Oh. So. I'm going to show you just, well, I guess we don't necessarily. Yes, we're going to have to because we need it for a normal force. That's the reason I did this. All right, does everybody see that Roy's force is going to affect our normal force? Mm-hmm. Although I guess it doesn't really matter, right? Because the work done by the normal force is going to be 0 anyway.
Well, won't it affect the kinetic friction?
Oh, right, it's going to affect the friction. Thank you. I knew there was a reason why I had done this. All right. Glad you guys are here. All right. All right, is everybody good with this? Does everybody understand that this is the 30 degrees? Right? Because it's below the horizontal. Here's my horizontal side. Follow? Okay, so the force of Roy in the y direction is going to be negative 200 newtons. The force of Roy in the x direction is going to be 400 times the cosine of 30. Gives you 346.4 newtons. Cool? So notice, just to be clear, this right here is really 400 times the cosine of 30 degrees, right? Follow? Right, that's f cosine 30, or theta. Okay, so let's make our free body diagram. So here's our box. It's got a mass of 50 kilograms. So, force of gravity is negative 490 newtons. Wow, I almost died. A rock almost fell on my head. Oh no. All right, we'll deal with that later. Okay, so as a quick note, you guys, in one word, never mind, I don't want to go there. Okay, so here's our force of gravity. I was going to say something about the test from the other day. Nope. Nope. Okay, so there's the force of Roy, in the y direction, right? Here's the force of Roy in the x direction. 346.4 newtons. Two more forces. What else? Normal force. What's the normal force going to be, you guys? 690. And friction, right? So it only gave us the coefficient of kinetic friction, so I think we can just assume that we overcame static, right? So 690 times 0.25 gives us 172.5. Cool? All right, so there is our free body diagram. Problems? Okay. So, can I erase this little triangle here? All right, so part A. How much work did Roy do? Well, the work by Roy is equal to the force of Roy times my displacement times the cosine of the angle. But look, FR cosine theta is really FRX, right? Follow? That I just combined this and this to give me this. Okay? And so the idea is, point for me, you guys. Do you guys all understand? The box is going to move that way, right? And so this force is the force that is causing the motion, right? So the force in the direction of the motion. So that's sort of what dot product accomplishes, is it says, you know, what's the effect on this vector by this other vector in that same direction? That's the worst sentence ever said by a human being. All right, here we go. 346.4 newtons times, what did we say the distance was? 6 meters. And so that gives you a big number that I don't know. 346.4 times 6. So you get 2078.4 newtons. No! Joules, joules, joules. Sorry? I don't know what do you mean. But, because here our angle is 0, is that what you mean? So here's the other way we could have done this. If I'd wanted to, I could have just done this original equation. So the force of Roy would have been 400, right? Times my displacement, which is 6 meters, times the angle between the force and displacement, right? So Roy's force is like this, the displacement's like this, the angle between them is 30 degrees. You could have. The only reason I didn't was I needed to do the three-body diagram. Hold tight for a few seconds to get the normal force to get friction. Okay? All right, so you guys, we'll finish these notes up tomorrow. We're probably going to end up making the next chunk of the notes due or the next chunk of the homework due Wednesday, though. Just as a heads up, all right? So you will have homework tomorrow night. So budget for that.